I'll start then. Hello everyone. Today we are going to do something a little interesting. This is chaos theory, and it sounds fancy. A lot of people like to use the word in very fanciful manners. We'll just go with. We'll start from the beginning and figure out how to get this thing done. So, so let's look at what. Let's start with something simple: functions. Right? If you have a function which is something like I actually just call it f. It takes a number and then return x minus 1. Very simple, right? Uh, Maybe so. Is my screen visible to everyone? Should I increase the size a little?
It's
Uh,
reading.
Okay.
Uh, j- Keep it increased. Actually, these days YouTube works on 420p on mobile devices.
Oh, okay, okay. This is, I think, the largest I can go without distorting. Right. Okay. So actually, I think I can go a little bit. Okay. So let's say we start with uh, x equals to 50, right? And we do f of x, and as expected, we get 49, right? And what happens if you apply this function again and again uh, in this fashion? You keep on chaining these things one after the other. Uh, as expected, you start seeing lower and lower values from these outputs. So if we take something like, let's take the first, um, let's say, list range of the first 10 numbers, right? And title 1 is equal to f of I for I in x. So you apply this function to these numbers once, right? And when you apply it once, and then what you do is create it dot plot x and iter 1. So you see this really nice straight line going on there, right? This is understandably just our function was just x minus 1. So whatever x you have here, say 2, let's add a. So if you had 2 over here, you have 1 as the final output, right? And if we increase the number of times we apply this function for n in range, let's say we apply this function 5 times, x equal. So let's say y is equal to f of I for I in y, right? So we apply this function 5 times, and we still get a straight line, although the line is now shifted, right? So for 2, you're suddenly getting minus 3 over here because you've applied function f. Let's make this a little cleaner. So you've applied function f to the value 5 times, right? So you're getting 2 shifted by 5, reduced by 5, which is minus 3, which is understandable, fairly understandable, right? Let's say we increase this to maybe, yeah, actually, let's just reduce it to 3. Let's see what happens with 3. So you reduce this, you get a straight line. You increase it to some huge number, 100, you still get a straight line, right? Even if you increase the actual numbers that you're calculating, you still get a straight line, right? This repeated application, यार ये jump बहुत कर रहा है. Okay, that should fix it. So this repeated application of the same function to its own output is called a map, the map of a function, right? What happens when you repeatedly apply a function again and again to its own output? If we do something else, let's say you take some r along with this and you reduce it by r instead of just one, right? Oh, ये क्या किया मैंने? Right, so you reduce it by r, and then here, let's say we set r equals to 1, just to stay with our original definition. Right? We still get this straight line. And then when we do r2, we are getting the same straight line, 3, it's the same thing, and so on. But these lines are going to be different, right? So if we plot, say, so you've got this, let's just copy this entire thing and plot it for R4 also. Right, so you've got this little thing going on, which plots two lines for you, 1 and 2, right? We'll just, so you've got these two lines going on, right? Even though R keeps on changing, these values don't really change. These values, the nature of these values is the same. They're all linear. Okay, let's, instead of this simple function x minus r, let's try something else. Even if we do plus r, we still see the same behavior. The y-axis has shifted, right? If we do x multiplied by r, we expect a behavior change. And then suddenly the rate of growth is different, right? Because the nature of the function is different now. And then let's say we do something ridiculous and x to the power of r, and I'm just going to start this again. So maybe just keep it 2 and 1.5 here, or actually not that also. So this is huge. Squaring takes up a lot of time, right? But we still don't expect any. Let's reduce this. Let's just take 10 numbers instead of. And then for those 10 numbers, if we still apply it 100 times, we still see the same things, right? Now here's, so what we are saying is basically, if we are given something simple, let's say if we have defined function x and r, right? Return x plus r, something like this. And we are also given how many times to apply. Let's say let's say 100. So, and we are given how many times to apply this function to itself. Usually you can directly just give an answer. So for example, this function, if applied n times, would give you x r minus, I think n times r. I think so, because this and then minus r minus r. Oh, sorry, plus r. So there is a final function which will directly give you the answer to whatever this thing is doing, right? And we can, when we plot that and see, that's exactly what we get. Because you take a list of 100 numbers and then you say subtract 1 from it, right? R is 1. And then you apply it n times, right? You get this thing. And then you also get So let's say GIR for I in X, and this is the G function. So you see these two are actually identical. There is absolutely no difference. You can maybe see if we make this X. So you can see a little bit of, I don't know if you can see it, a little bit of red behind that. So yeah, these are essentially the same functions. The idea is that if you know how many times you have to apply it, uh, you can usually formulate another function which gives you that exact answer without having to apply this first function those many times. So you get an analytical solution to this system. Now, where chaos theory begins to differ is one of the classic examples of this is r times x times, let's just start with this, right? So you have x equals to a range 0 to 50 maybe, right? And then y is equal to say f of x times r. What do you want to do? So let's do r values. So you could take and then so what this part of what we are trying to do here is see. So okay, let's do it like this. So you have x by r, right? And then you have x is equal to np range 1 to 100, right? And let's say you have y equals to, you remember that trick where you had any number, some ridiculous number, and if you keep on dividing it by 2 in computer systems, you start to get closer and closer to 0, right? The this kind of a thing, this behavior where repeated application of a number, of a function, irrespective of where you started it from, going to some place, right? So if you take, let's say, for n in, it doesn't matter what number, let's take 100 numbers, right? And we're just going to call that x. And let's say k. Let's divide it by 2 100 times, right? We are going to end up near 0. That's the idea. So what that behavior of always tending to some point is what is called as an attractor, right? So what here, so chaos theory basically when actually बड़ा boring सा हो रहा है अभी ये, but this really starts to get interesting here. So you have some function like x and r, return r times x times I think 1 minus x. I'm not sure. This is your function, right? And then what you do is n times is 100, and then you say n samples is equal to, let's say, 500 samples, right? N tries is equal to try 10 different times. So you get x final vals equals to this. So for trial in range and tries. So what you're going to do is you're going to generate random values of r, right? Uh, and we are also going to generate random values of x and try and figure out where this X value is going to land depending on where it started from. So you have for in samples, right? You don't really care where you start X from. Actually, you can just do this X equal to random dot random, right? And then what you do is you take R. So for R in np dot a range, let's start with 0, go till 2 in samples, and you get X equals to f of X and R. Final values dot append X, that's dot append R. So here we would take R, here we would take X. ऐसे करते थे क्या? नहीं. I have this written down. Wait. Should never do live coding, man. So this one, yeah. So you have this part. So the equation is still the same. You get, okay, we're just going to get rid of this part. N trials, how many times should we initialize it? N steps, range, and here you have F, right? So let's, since we have not typed it, ये फटाफट देख लेता हूँ एक बार. R should be 0 to 3, and then 3 to 5 is really fancy. So this I'm going to so अभी के लिए we'll just stick with a small space. Values of R goes on the x-axis. Final values after repeatedly repeatedly applying this function goes on the y-axis. We do this 10 times, 10 different 10 different trials, random values of X, right? What we see is something really interesting. For 0 to 1, essentially nothing happens. Repeatedly applying the function doesn't do much. 1 to 2, we see some curve kind of thing going on. Nothing exciting yet, है ना? क्योंकि ये तो this we can predict directly if we know the original equation and how many times we have to apply it, right? What starts happening though is 1 to 3, you see this arc going on, right? This is nothing fancy. But then suddenly after 3, you start getting this beautiful, let's go till 4, increase to 500. You suddenly don't know, right? That's the beautiful part. So let's just focus on this 2.5 to 4 range. I'll just reduce the range to that, right? See, now what we are having is, let's say 3.2. Okay, if you set R to 3.2, it doesn't matter what X you start from. After 100 applications of the function, you are either going to be here or here. Okay, before 3, it was just one thing, one attractor state. Let's say R is 2.8. It doesn't matter where you start from. You will end up at, what is this, 0.65 or something, I don't know, right? But then suddenly you have this bifurcation going on. At R value 3.2, you cannot predict where it is going to end up, either here or here, right? And then you so as you go further and further into the system, you see here there's another bifurcation, right? So any value at say 3.45, it is either going to be in this branch, this branch, this branch, or this branch. 4 possible values, and you cannot predict which one, right? You can, the only way to know which one is to actually calculate it. There is no quick analytical solution to get that out. So if we do the full graph, this might take some time. You get this kind of a graph. The first bifurcation, the second bifurcation, and then what you see is this sudden period of chaos. So let's just focus on the 3 ke aage wala part. So if we render that, mm, you see some points. ये faded सा क्यों आ रहा है? Okay. इसमें there are some points which so you have some clarity here, some clarity here, and then some regions are there which are just pure chaos. ये यहाँ पे you can't predict anything, right? This can go anywhere, and then suddenly you have moments of clarity where an attractor state is again present, and then again it is gone. It is all chaos again, right? So this is what chaos started with. If you have a function, repeated applications of that function will lead to a map, and the map, the final values of the map are extremely sensitive to where you started from, the initial value. So an initial value of say 3.8, and you are in full chaos, you can't predict anything. And let's say let's assume this is 3.85, I think, I don't know. And let's say 3.85, and suddenly you have clarity. You have only 1, 2, and 3 attractor states, right? So this kind of, I will say, hypersensitivity to initial values is what chaos theory is about. Uh, you That is where the saying that butterfly flaps its wings somewhere, hurricane happens somewhere else. The idea is that the initial conditions were dependent on how the butterfly flapped the wings, and then repeated application of some function led to a hurricane somewhere else. That is the core idea. So this is what chaos looks like, and chaotic systems are everywhere around us. If anyone works in cryptography, they would know any source of non-repeating information generates entropy, right? Uh, and chaotic systems are actually very entropy rich, because unless you know the initial value, there is no way you can predict what is going to happen next, because this guy could be at, let's say, point 2 at this moment, and then suddenly point say 1, and then next moment somewhere else. So it's highly unpredictable, right? So you get these kinds of systems. Chaotic systems are also present physically around us. When you know that uh, tap having dripping water on it, like tup, 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 that certain configurations, that becomes a chaotic system, and you cannot predict when the next drop is going to happen, right? And because, so original research for chaos was actually based on that. They were recording water drops. uh, well, that famous scene in movies where you do defibrillation, I think it's called, when you shock the person whose heart has stopped. The idea is also, I might be wrong about this medically, things might have moved on, so please check. But the idea was that the heart, the heartbeat is a chaotic system, and as long as it is settled in an attractor state, let's say, what is the average human? I don't know. Let's say 1 beat per second is healthy. Let's say, as long as it is settled in a attractor state, it is good. You are going to get your heartbeat for your entire life. But what if the initial value was wrong? And let's say after 50 years, suddenly this heart is going to go into a chaotic state. So what you're trying to do there is shock the heart and reset or restart from a different initial position. hoping that you're going to end up in an attractor state again. So those are some really cool applications of. Yeah, sure. Harsh wants to speak. Please go ahead. Oh, chaotic pendulum. Someone's put Manav has put a link in the chat. Harsh, are you speaking? I can't hear you. Okay, I'm just going to go ahead. I don't think Harsh is speaking. Okay, so moving on a little bit, uh, let's look at. So that's where chaos started from. Uh, and another.
Hi Arjun.
Yeah, yeah, sure.
Sorry. Uh, Actually, I was saying like that graph looks like the fractal graphs.
It does, doesn't it? How do I undo this thing? Yeah, this one.
Yeah.
Yeah, this is known
But
as the bifurcation graph.
okay, but that part is very surprising that where everything is empty when it is bifurcating.
This part.
Yeah.
Yeah, that is really surprising. This is one of the simpler functions. The logistic. This is called the logistic map function. There are other functions which display even more beautiful chaotic behavior. Uh, I'll show you a fractal later on, which is really nice. I really like it, uh, and it's completely unexpected. You don't expect that this is the pattern that will emerge, right? Another thing which probably I think I forgot to mention, chaotic systems uh, when they are looked at. le- Okay, let's talk about that after we have discussed fractals. So, like you just said, this starts us on the journey to fractals. So, the fractals basically started as uh, I think a good story for fractals would be coastlines. If you have a country's coastline, how do you measure it? Let's say you have a 1 kilometer uh, ruler, and using that, what you could do is place one end on the coast, find the next end, mark that as 1 kilometer, go again and again and again and again, right? Uh, so you would have some measure of the coastline. And then let's say you had a 1 meter ruler and you measured the coastline using that. Suddenly, the length of your coastline would increase, because what would happen is you would have things that you had skipped, assuming that they are a straight line, would suddenly start showing up as a. Can I do a? Oh, I can't do a pen. Oh, never mind. Okay, I thought I could do a pen here. Okay, so the idea is that if you measure using a smaller unit, the thing that you are measuring sometimes leads to a larger quantity. For a good example is a coastline, but it's not very visual. But I don't know how many people would be able to visualize it. Another example could be football ground, right? We have all measured using, how many steps does it take to go from one end to the other, right? Uh, so let's say it takes 40 steps, and each step is some. You convert it to some standard unit, you get 100 meters, right? Suddenly, what you do is, instead of steps, you take a smaller unit of measurement. Say you are measuring with a scale now, 15 centimeter scale. Uh, Now, instead of 100 meters, what you're getting is 100 meters and 25 centimeters, let's say, right? So if you reduce your unit of measurement, you could end up in a larger quantity than before. That is where the idea of fractals started coming from. Are there geometric shapes which, when you are plotting on a graph paper, and you zoom in, you suddenly start seeing more detail, right? Are there geometric shapes that exist like that? Every time you zoom in, you can get more and more detail. So, one of the most famous touch snowflake. This is really cool. What you do is you start with a triangle, and then you start. You know, there is a procedure. You keep on applying that, and you start getting this snowflake, right? And here is the zoom. This I really like this part. So you can keep on zooming into this picture how much ever you like. You're always going to get something. It is never going to finish, right? But it's always going to be the same also. So it's not very interesting that ways. It's a repeating fractal, right? So you can see it's a repeating thing. Uh, at least the basic thing is repeating. You could have complex things. Now, where this thing becomes very interesting when it meets chaos theory. So you have something. I'm just going to borrow code from here. So what we're moving on to the Mandelbrot set right now, and it's a fairly simple idea. Let's say you have a number n, right? It's a complex number. Complex number means we can put it on x and y. We can plot it on a plane, right? You take this number, and what you do is you just like before, you take a number and r, and you compute something. That something is this thing, right? So you take I think this is z, this is x, right? So what you do is you take x and you calculate this quantity, right? And you can just return this part. Am I doing this right? Yeah. So that's what you do. You basically square the number and add a constant. Square the number, add a constant. And what you expect and what you test is if the number exceeds a certain boundary. So or say if it becomes larger than a certain value, you just say it is no, I don't want this number. And if it stays within that value, then you say, yeah, this is a good number. Keep it, right? So you get this little function which takes a number, check if a number is good or not, right? And this is what you get. What you can then do is basically if you have dot nothing, so you have this plane, right? You can start taking x values from a certain range and you can start taking y values from a range. Each of these points is a point in the set, right? And what you end up getting is for each point a yes or no decision. Sorry about that. So you get a yes or no decision for each point, and you can color it using black and white and so on, right? This code is already present in this repo. I will just paste the link here. So we'll just open that up. So here's the function. You take a number c and you want to check if it escapes the a circle of radius 2, right? And you say that okay, how many times should I apply this function? So we apply it 100 times. The function is fairly simple. You just square z. You start at 0 0, and you square it and you add c. Square it and you add c again and again, right? And then what you do is for each number x and y, for each complex number having x and y components, you say that has it escaped or not, right? And then you plot it on a uh, basically just plot it on an image, right? Image, and did it escape or not. When you do this, you get something interesting. So I'll just run that code. 8080. You get this really nice image, right? Uh, this is the Mandelbrot set. Everything inside this completely black part is the Mandelbrot set. Everything which is not black is not the Mandelbrot set. And what we've done here is basically colored black or gray according to how many steps it took to escape. So you see, we can close this. I think this part is also done. This is done. So you see this part where it said end to escape, and we are using like returning how many iterations it took to escape the boundary. That part is what we are using to color this grayscale image, right? So you get this shape. It's a very familiar. If you plot it in just black and white, you get this thing, which is similar to what we are getting here, right? Now, the nice part is you can actually zoom in on any part of this thing, and you will start seeing more and more detail, but it never repeats. That's the beauty. It'll be similar, but it will never repeat. So at this point, you can almost see the rotated Mandelbrot thing, right? You go further, further, and you're going to start seeing the same thing again and again and again and again. And then you start seeing these little islands, right? And then when you go there, you discover that, you know, oh man, I think I went into the wrong island. But you can actually discover the original set within this, right? And so let's look at this part. This is really interesting. So if we have, let's say, this is what I was talking about when I said coastline. Right now, we are only doing 100 iterations, right? If we add, let's say, I increase it to 300, we get a different picture, and you can see the slight difference. I'm not sure if you can tell on video or not. Okay, so you can see a slight difference in the boundaries, right? The more you measure, the more detail you find. That's the whole thing. So this thing is called one second, let me just go close the door and come. Right, so this thing is called the Mandelbrot set. I think I've said it a lot of times. So we start with the original image over here, and you can keep on zooming in and so on, and you will get the same set repeated in the details of this image. This is all very nice, but how does it tie into our original bifurcation graph? That's so. I will leave you with one link over here. This one has a much better view of the Mandelbrot set, and you can explore it a lot better. You can just draw this boxish kind of thing, and it will redraw on your browser. and then you start seeing this little island, and then you rediscover the Mandelbrot set again, and then you go further in, and so on. And there's a little set over there, right? So you start seeing this self similar, but never the same behavior. You see, there's a small set here. You go there, and it is something. It's different, but it's, yeah, similar. It's not exactly the same. Now, here's the kick part. uh, this image that we are seeing, right? It just blows me away, actually. So this part, how does it tie into the biograph, the graph that we just saw? Where is that? Where is that? How is this graph related to the Mandelbrot set? I think you just saw that. So on Wikipedia, you can see this really nice image. The Mandelbrot set, when you plot it in the third axis, you can see the bifurcation graph there, right? Uh, the original bulb is, it's inverted, as in our original thing, the bulb was on the left. So
Um,
this is the big bulb.
Sorry to interrupt, but what do you mean by plotting the third axis? Like we need one more variable now for plotting in another axis.
Yes, we do. Good point. I was just going to say that. Uh, you see this, where is that equation? Uh, you remember that equation which said whether it is in the set or not, right? If it is in the set, we are saying it did not escape. And here we are just setting a default value of 0, right? Instead of this, if we actually return the magnitude of z that we got, that is the the third axis, the third number, right? Does that make sense? So all of these numbers, the black part, they are black because we set them to 0, right? We said 0, that's why all these things are black. Instead of that, we could plot those numbers in the third axis, the z-axis, and the numbers would be whatever the final magnitude of this z is. We could just do abs z and plot it, right? So
Got it.
that would give us this three-dimensional plot, and which ties us back into the bifurcation uh, plot. The main bulb is single, there is a single value, right? And then you have two potential values for the second bulbs, and then you have four potential values for the next bulb, and then it's just chaos at the end of it, right? So this is a really, I really liked this. I don't know, I just find it beautiful. I have no reason. Okay, so this was there, and then the final, the beautiful fractal I was telling you about. There is a fractal called the Buddha brought, right? It just looks like a Buddha which is sitting there and meditating. And if you can, I don't know if you can see, this is actually also self-similar. You can see a mini Buddha over there, right? So you have this, I don't know, infinite Buddha fractal, which is there. Yeah, so that's all I have for today. Chaos and what all we can do with it. So yeah. And any questions? Anything you'd like to discuss? I think we should do it now. We took up a lot of time.
I'm still confused about that part. When we rotated the that fractal, okay, so we got our original graph, which looks similar, that bifurcation graph, which was
Yeah,
very similar. Okay, but
yeah.
when you were showing that bifurcation graph that was made through this fractals z-axis, I was not able to see that part where it was missing those points.
Uh, yeah, yeah. Do you mean how do you get that? How do you get this picture? That's what you're asking, right?
No,
Okay.
not exactly this. You go to original bifurcation graph that we made.
Okay. say this is here. Yeah,
Huh. So that part now which is empty when it is bifurcating too much.
yeah. This
Yeah.
piece part. Yeah.
I'm still confused. Like, what do this mean? And like, why it is there?
I
Like,
don't know, man. Mm,
I am very confused about this, and like, it is. It seems little bit interesting, and also like, I was not able to say it in the visualization that you were showing the 3D one.
oh, this piece part. It's in the tail. So if you look on this side, it's very faint. But I'll just put the link in the chat because you might not be seeing this over video. Uh, so probably in this part of the graph, that is where you're probably going to see the peaceful region, right? So if you look here, this is the first, second, third bulb. So first, second, third bulb, and then the piece comes over there. Yeah. So this is probably this little. Okay. So this little dot over there, that is probably where the piece thing is. If you can see in the image, once it rotates that side, you can actually see it. There's this long vertical which is there. As for why it happens, I don't know enough theory to answer that correctly.
But it would be like a very interesting answer. Actually, I saw a very similar video. I will try to find it. Um,
Okay.
Meanwhile, we are having this conversation.
Hello. Ah, yes. Okay.
Let me find it.
I think Jasmeet posted a word. Oh, I think I linked to this if I'm not wrong. Is it this one? No. Okay. Yeah. So this was a Zoom video I had found, which really it was really nice. So the link is in the code. Okay. So this is not just this is not the only application of. So I remember one parameter is I I don't know. People who are in machine learning will this will really kick your uh, imagination. So in neural nets, you have this thing which says n parameters, 1 million parameters, right? And so on. Model complexity is measured using parameters in lots of places. This one paper showed, is it Rochester? Yeah, okay, this is the one. So this guy learns a single number, and what he's learning is a parameter to a chaotic equation, and he's able to. I don't know if it's a he or she. I don't know. Looks like a he. They're able to basically fit any data set with just one number, one parameter. Of course, there is a caveat. You need very high precision on that, but still, chaos has its uses there. So this is just a very interesting topic that I found. Yeah,
Can you share the link?
yeah, I will just put this. Okay, I've put it in the chat. I'll also update the repo. Yeah, I put it on the repo also.
I'll
Okay.
share the link of the YouTube video that I was speaking about.
Okay. Actually, can I copy? Okay, no.
The
This
full title of this video might be something.
three blue. Yes. I like three blue. This one, yeah.
but it's not a good idea to play it over here.
Yeah, I'm not playing it. I'm just showing it. Yeah. Okay. So, okay, I guess I don't really have anything more. Uh, so yeah, that's mostly it.
Okay, so I will end the stream. Thanks everyone for joining. So let's end this session officially.